It takes me a little bit of time to move them from Piazza onto my iPad so I can view them. But anyways, I'll go through the problems. The one person wanted me to uh, discuss reactions from the courteous rearrangement. So we'll start there. Um, there's different reactions that can take place from the courteous rearrangement. So the courteous rearrangement is when we have an acyl azide and we heat it up and it goes to an isocyanate. Oops. So in order to see the reactions of isocyanates, really we needed to kind of go back, I think, a previous lecture where we talked about making isocyanates in a different way. You're able to make these from phosgene with one equivalent of an alkylamine to make the isocyanate. And this is where we kind of discussed the different types of addition reactions that can take place. And so that was sort of the question, what happens if only 1 molar equivalent is added? You end up making an isocyanate with phosgene. And these generally will be simple addition reactions. So visually, we have an alcohol. It'll add across formally the carbon-nitrogen bond to give us a product where we make a carbamate. These are also called urethanes. You may have heard of polyurethane. These are the linkages in those polymers. Or if we add in an amine, we make a urea. And so I'll just walk through these different possibilities. The third option is if you add water, and that was specifically the case we see most frequently in the Curry's reaction rearrangement when we want to make an amine. So isocyanates are very electrophilic because we see that we have this dipole going towards the oxygen, and we have a slightly weaker dipole going towards the nitrogen. So definitely this center carbon will be quite electrophilic. If we draw out the isocyanate, in this case we had a phenyl. We can have the alcohol add in. These can be catalyzed by base as well, where you'd be deprotonating the alcohol first. That's usually faster. You can still get these to occur because isocyanates are quite reactive anyways. And we end up making an intermediate where you can formally put this charge on the oxygen or nitrogen. I'm drawing it on the oxygen just because it's more electronegative, but you can appreciate that there is a resonance structure that would put that charge onto the nitrogen as well. And then essentially there's just a proton transfer. Proton transfer. Where the hydrogen will go, oh, red's too angry, from this oxygen, and then it'll be protonating that nitrogen. If you protonate that nitrogen, formally it'll be a positive charge on the nitrogen, but since we have the electrons from the oxygen, it's a negative charge, these will be able to come down and take a proton from wherever it needs to. The exact same process can happen if you add in an amine. We'll do our addition and make this zwitterionic intermediate. Amines add in much more quickly because they are more basic. And then proton transfer will give us now a urea. So this is a carbamate. This is a urea. And these are the two major products that we would get from the addition across an isocyanate. There is a third option, and I'm just going to copy and paste what we had before and modify it. And that's the addition of water, because something else can happen if we use water. I can move that up there, give myself a little more space. So again, the exact same process happens with water. Only now we get an intermediate called a carbamic acid. And these are unstable. These will very quickly lose CO2 and you just get out the free amine. So these you won't be able to isolate or use in any way. They pretty much just briefly exist and then they go to the amine. This can be acid or base catalyzed. The mechanism never really looks pretty, but the driving force for carbon dioxide loss is very, very easy, and then it bubbles away. This is just the reactions of phosgenes, so I think that's a slightly separate question. We can go move to some questions that were just posted on Piazza, and I saw another one just now. I'll try to get to that too. If there's any more while I'm here. No. So the first one is a synthesis question. I think this was on a prior exam or practice exam, something like that. And just kind of talking through this problem, like how do we, because at first we don't know what this initial starting material is. So I think the question might be better, like how do we think through this problem to get to the right answer? So one of the giveaways, and I think this was in the section where we're learning about Grignards and their additions to esters, there is a sort of giveaway here in that if we were to draw out ethyl magnesium bromide, we can note that this ethyl one is in excess, and we have this ethyl group here, and that appears twice in the formation of a tertiary alcohol. So usually if you have two of the same alkyl groups attached to a tertiary alcohol, this will give you the notion that it's in some sort of addition to an ester. So if we have any sort of, this could be a lithium or Grignard. I'll say phenyl to make it different. It could be a methyl ester. These always have two additions. And we make a tertiary alcohol afterwards. So we want to imagine this tertiary alcohol actually going back to becoming an ester. So we have this type of structure. But one question is we end up having this alcohol present. And so one question is, what do we put on this alcohol? If we add in a Grignard, it can be deprotonated, so maybe that'll be fine. If we have excess, then it probably won't hurt. We can make an alkoxide during a Grignard addition reaction. So in this event, first you added in the RLI, or Grignard. We're talking about Grignards. We'll keep it as ethyl Grignard. ET. Could we think it'll deprotonate and that alkoxide wouldn't stop the addition to the ester afterwards? It's pretty far away. But alternatively, you could try to connect this oxygen directly back to that ester. And even if you deprotonate that alcohol, we would see a very fast cyclization. So there's really two different ways you could try to solve this problem. I think going back to the ring structure is a more difficult thing to see, but it will give you this lactone. And then the next thing in the problem is that we have MCPBA, and we have an ester, so that means that this is probably for a Baeyer-Villiger reaction. So if you imagine the Baeyer-Villiger going backwards, we just need to remove this oxygen and turn it into a ketone. And you'd get something like that, which is what's written in the box. If you wanted to try to apply the same rationale to the acyclic molecule, there's a couple changes you could make to the structure. One thing we know is that whenever we go back this way with Baeyer-Villiger, we'd make some R group here. We have the alcohol. Now we know that we need the migration to occur specifically at this bond. That means we need to have some sort of R group that'll be bulkier or better stabilized positive charge than the linear alkyl chain. So one possibility would be something like a dimethyl group. This would increase our substitution. And it would also give you a better chance of having the migration go the way you want it to. If you really wanted to, maybe you were concerned about this alcohol, you could even do something like draw the acetate. This is a non-obvious way to probably approach this, but if in the end you do the Baeyer-Villiger, the ester won't do any more reactions, and then the ester will end up getting cleaved by the ethyl Grignard anyways afterwards. So this is probably the best solution to the problem, or the cleanest one. But you could go in with the alcohol or something else there as long as it was removed in that reaction sequence. How did the cyclization happen? Well, the cyclization doesn't happen, you start with the cyclization. Or do you mean how did it ring open? So if we have ethyl magnesium bromide, it'll add into this ring. This tetrahedral intermediate will be able to collapse. It'll be a reversible exchange, but as soon as we make this ethyl ketone, it'll get attacked again by the Grignard. And then after workup, we get the tertiary alcohol. And the Baeyer-Villiger on this molecule is nice because either direction it goes, it's a symmetrical molecule, so you'd always get the right answer. So this is another problem I was asked to walk through. This is kind of the solution all drawn out, so I just abbreviated it so that I can kind of draw all this out again and maybe talk through it. So we're looking to try to figure out where does, as always, where does the starting material appear in the product? And so probably this methyl group here is our giveaway, and we kind of track it around from there. No, stop going to a straight line. So we have a 4-carbon sequence there, and so it's this methyl at the end that gives us an idea of where this starts. And so this is where this molecule comes from. We also see that we have this ketone here, and we have a hemiacetal there, so it's in the right oxidation state. So it's always hard to see how to make a cyclic hemiacetal like this. It's always best to try to break it down into its ring open form. That always helps synthesis thinking and planning a lot more. So we know that hemiacetals, and this is still an equilibrium process with acid or base. This will let us ring open. We can count our carbons if we're getting concerned. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Means attached to this will be our phenyl ring and also our alcohol. That's our 5. So now this is the molecule we need to make. And this looks a lot more similar to our starting material. Now we can see our carbon sequence appear once more. So now somehow we need to make this 4 to 5 bond. So in this topic especially, we learned that in order to make a secondary alcohol, we want to do some sort of organometal addition to an aldehyde. So we're going to break this bond and go retrosynthetically backwards again. I lost a carbon. Did I lose a carbon? No, I didn't lose a carbon. No, we're good. So this is the hypothetical Grignard we want. But this Grignard can't exist because we have incompatible reactivity. Something else we learned in this section was a protecting group for the carbonyl that would let us protect a ketone by turning it into an acetal, because acetals are stable to basic conditions. They can only be made and destroyed with base. But this is the visual of the general reaction we want to perform. We want to have a Grignard like this turn into the aldehyde. And that means we need to go and actually have a protected ketone. It could be any type of acetal, but these cyclic ones are particularly easy to make using ethylene glycol. I was confused what would happen to the ether oxygen. So if we look, I'll make a little thing in the corner. So when we do this, the middle carbon, the carbon that's attached to two oxygens, the incompatible part is a Grignard can react with a ketone. I'm pointing at both, but it really would be like this would attack this. It probably wouldn't be intramolecular, but Grignards react with ketones very quickly. So you wouldn't be able to make a Grignard with a ketone on the existing molecule because they would immediately start to react with each other before doing the reaction you want. What you can do is put in a protected version of the Grignard, and that'll be safe. So when we're going back to the acetal or hemiacetal breakdown question, and you approach the logic more or less the same way, this originally means that it was a ketone. And so if we redraw this molecule, all you really need to do is turn this into a ketone. And then the two other molecules essentially go back to, can be broken apart and imagine just becoming either two alcohols, in one case water and an alcohol. In this case, this OH is sort of insignificant, but we always want to have the one that is going away from the carbon become an alcohol for sure. You could say then, H2O. So this is a good way to just try to remember. We can think about the forward or reverse reactions. If you were to add acid to this, this would be protonated. You could have this carbon come down. It would break apart, if that helps you think through this a bit more logically. This will be positively charged. And you'll see the alcohol leaves. And this is how I came up with this structure here. Cool. And so I'll go back up to this other one since I already have it all written out. If you do this in the forward sense and you're planning, now we'll want to protect it first. So this way we can then, we're going to use our ethylene glycol. This is our best diol for protecting an alcohol. We're going to use toluene because it's dry, helps us remove water, and an organic acid that'll be soluble in toluene. We're going to make our protected bromide. We can make the Grignard. Now this is safe from reaction with the Grignard. We can add in the Grignard. It'll attack to make our secondary alcohol after workup. And then in the process of trying to deprotect the acetal, we're already going to use acidic aqueous conditions. This will make this intermediate along the way, and the alcohol will be able to add in. This also is a reminder that these 5- and 6-membered cyclic hemiacetals are quite stable. Okay. Move it along. I almost missed this one because it was in between the big pictures. There's a question of how does thionyl chloride replace an OH with a Cl? In this case, yeah. Oh, you could use zinc in this step if you wanted to. But zinc does, but you would not be able to use it here. This would still be incompatible. Zinc doesn't, organozincs don't react with esters, but they will react with ketones. So you'd still have an incompatibility problem. There's not much of a way to get around using a protecting group in this example. Oh, but I mean, so just to be clear, are you looking for this mechanism or this mechanism, the alkyl alcohol or the carboxylic acid? Because both technically convert an OH to a Cl, conceptually similar. Okay. In both cases, we can go do that. So in class, you mentioned how there's two different conditions. One is with pyridine, one was without. We're just going to talk about the pyridine case. And it ends up getting a little bit longer than you want it to because there's these extra steps at the end. The general idea is that thionyl chloride does have a lone pair on the sulfur. So you can't, and so it means it's sp3 hybridized, it's tetrahedral. That means geometrically we can do an SN2 attack on it. Generally, we'll have pyridine around in these examples as well. And since we have pyridine, we can go and take this proton away. We make this chloroalkyl sulfite, which you guys don't need to know the name of. But pyridine actually serves two purposes here. It can both act as a base and a nucleophile. It's similar to DMAP in that way. Usually these are like run in pyridine. This will do another SN2 reaction. And people do this to help the stereochemistry. I think empirically long ago they found that if you use pyridine as the base, you get full inversion, whereas if you use no pyridine as base, you do not see an inversion. So maybe we can emphasize this a bit by adding in a stereocenter. So along the way, we have that chloride leave. That is now going to be our nucleophile. And it's able to come back, and now this is a very good leaving group. We have a positively charged amine. This now can do an SN2 reaction. No. Where now we're going to lose SO2 along the way. We're going to invert that stereocenter. No, PBr3 is simpler. PBr3 doesn't have this funny business with pyridine. The issue is that, and this isn't even true all the time, there's some weird mechanisms where if you don't have pyridine present in this reaction, you end up getting a stereoretentive product. And they say it has to do with it's sort of an intramolecular displacement from this sort of intermediate. It's kind of weird. PBr3 has a nice two-step two-step mechanism. It happens in a very similar fashion. It's just a lot shorter. So we can have the alcohol do an SN2. And now the counterion bromide directly does the next SN2. And this is always with inversion. But if you see SO2 in an alcohol, I'll have pyridine there and it'll be inversion. So you don't have to worry about this funny business. Yeah, PBr3, what a great reagent. So simple to draw the mechanism. What else do we got? I haven't read this. I was just copying and pasting. I see two orbital interactions here. the double bond electrons reaching for the oxygen and the oxygen's electrons reaching for the double bond. Oh, so there are two orbital interactions taking place. I think I said 220 for the submission, but yeah, 1120 release, 220 submit. I would still accept exams afterwards if there's the technical difficulties. Hopefully there will be no, with the extra time, hopefully that's less of a pressure situation. But again, we're looking to get everyone's exams in safely. Just do some good old-fashioned organic chemistry. Yeah, so there are two orbital interactions in the epoxidation. There's only one of those two sets shown in the picture, because we only see the sigma star and the pi orbital of the carbon-carbon bond. There is one that takes place, I'll draw it out, where you can have the lone pair of the oxygen it can interact with the pi star of the carbon-carbon bond. So this is the N of the oxygen. This is the filled orbital. So this is another HOMO-LUMO interaction. Since you end up essentially making two different bonds in the epoxidation reaction, you need to have two sets of orbitals happening at the same time. But I just chose one so that people could see what the relevant orbitals were by the symmetry of these two pi groups being in phase and these two p orbitals being in phase. So that's a filled pi orbital, and you can see the linear alignment of the orbital density going through the two oxygens, and we have 1, 2, 3 nodes that are indicative of the sigma star. All right, I'll go pull up the next question. What is the major product expected from the following reaction? Have we used S- in any reaction besides the nucleophile and SN2? S and AR reactions we have, I think. So this is the reaction that was asked about. We just talked about the PBr3 reaction. So we know that the first step with PBr3 will be the inverted bromide. And then we have sodium methylthiolate, and DMSOs are a good giveaway that this is going to be an SN2 reaction. The only other time I would probably put DMSO as a reagent on an arrow if it's not an SN2 reaction is if it is a Swern oxidation. But you would see oxalyl chloride there too. So thiols and thiolates in particular, are some of the best nucleophiles for SN2. Thiols are quite acidic, they're big and polarizable, they're wicked fast. And this will be an SN2, so we'd also have another inversion of stereochemistry. The only other place where I can think we have seen a thiolate used is in a nucleophilic aromatic substitution reaction. So these also, I shouldn't draw the circle. These are also very good nucleophiles for SNAR. And then the fluoride gets kicked out. I think these are the only two times I would be adding them in as reagents. Okay. There's another person who said something. Let's did them. Okay. Can you write out the steps for number 7 in exam 4? I can do this. Let me go find it. Number 7, exam 4. Okay. All right, so this is the question. We have a carboxylic acid, and this gets treated with thionyl chloride. If anyone's curious about these individual mechanisms or things like that, I can draw them out separately. I'm just going to write it down as I go. We have sodium azide and heat. So this will briefly go through our acyl azide that then with heat goes to an isocyanate. Note that there used to be a carbon-carbon bond here, and now we have a carbon-nitrogen bond. And then we add in so this is what we just discussed at the beginning of office hours. But this can attack in, and then after proton transfer, we make this urea. We have an ethyl here. That was answer A. Yeah, so this is acid chloride formation. I think the tricky part on this question is making sure that you notice that the carbon does the rearrangement and we have the right carbon-nitrogen bond connectivity. Can I go over practice exam 3, number 5? I am on it. Let me look it up. Okay, I'm getting more questions. All right, it'll just take me a minute to go get all of these questions. Practice exam 3. Oh wait, this is the extra practice exam 3. Okay. So this is the question for exam 3, number 5. We have this long string of questions. PBr3, Mg, 4 we have acetone. All right, so we have this long string of reactions. I'm going to go look up exam 2, problem 7, just so I can copy it over real quick and we can do both in a row. Oh wait, we just talked about that one, didn't we? Okay, I'm going to go back up here a bit. and see, because this kind of correlates to what we just talked about, because we actually ended up showing both of the orbital interactions. It says, how do you know that the electrons are from the lone pair and not the sigma bond? Is it from the orientation of the orbital? Um, Essentially, yeah, you can see where the bonds are because they're kind of drawn in. You can see the line that would connect the two oxygens together and the oxygen to the hydrogen, whereas we can also see the lone pairs coming off to the sides of the oxygen. So that tells you that it would be from the lone pair of the oxygen. The other, I think, giveaway would be that um, yeah, there's not really a bond going in that direction. So I think there is a geometric element to it. And and also since you have a node in the middle, you'd need to have slightly different symmetry for it to be a filled sigma orbital or a sigma star orbital. So a filled sigma orbital um, would always have two nodes. We always have a node here and here with one filled in the middle. So this would be sigma. Um, Whereas if it's just a p orbital that houses a lone pair, or just a single sp hybrid, then it generally looks like that. All right, cool. Now I can answer this question. Okay, we got this long string of reagents. First, we have lithium aluminum hydride. Sorry for skipping, since we wanted to try to continue that thought. Oops. So the first reaction is going to have lithium aluminum hydride attack the lactone. This will collapse. We're going to make an aldehyde, and more LAH will react with this to reduce the aldehyde. And then on workup, we're going to make a diol. We started with 4 carbons, we still have 4 carbons, so we're good. This diol with PBr3, we're going to convert it to the bis bromide. I didn't say how much magnesium was there, but we're going to assume excess magnesium. At least that gets us to the right solution. So having there at some point in time, you have a Grignard on one side and an alkyl halide on the other. Grignards still aren't very good at doing SN2 reactions. Orbitally, this would make a 4-membered ring, which would be slow. And it could also act as a base to eliminate, but that's also going to be sort of geometrically difficult to do. But you can make these types of double Grignard reagents. And each of these will be able to attack their own molecules of acetone. We have our 4 initial carbons. We're going to add on an acetone to each side. They make tertiary alcohols afterwards. 1, 2, 3, 4. So now this is this one. And that'll give you this double tertiary alcohol. I'm not, oh, for the person who wanted me to write out the steps, I'm not sure which steps they wanted me to write out, if they wanted a mechanism or not. But hopefully that is good enough for number 7 on exam 4. Oh, ether's a solvent. That's it. Sometimes people use THF as well. It ends up being a nice solvent because the oxygens are Lewis basic, so they help to kind of coordinate to these metal salts. They help to keep them in solution. they can change the reactivity slightly of different types of reagents, but we never really talk about that. Yeah, that's why a lot of times whenever I write these things, I'll just leave off the solvent because unless it's playing an active role in the reaction, people will usually overthink what it's doing there and panic. So I try to only give you the relevant information. But then sometimes I leave out things like workups. That is relevant information at times. All right. What else do we got in here? Exam 2, problem 5. Exam 1, problem 3. Let's go to exam 2, problem 5 first. Oh, I think I have exam 2 open. Okay, so exam 2, this is asking about the fastest SN2 reaction. So we have triflates, we have mesolates, triflate, tosylate, and another tosylate. So we had these 5 structures. I believe this is the right question. So when we think about SN2 reactions, there's a couple of things we want to think about. One is sterics do impact SN2 reactions. Primary alkyl halides or things with good leaving groups always occur fastest. Ones with more steric bulk like secondary are much slower, and tertiary doesn't really happen at all. So looking at these options, we can kind of get it down to just the ones without the extra carbons. They're just going to slow down an incoming nucleophile. Then we get it down to really what is the nature of the sulfonate that is here. So all of them have this in common. All of them have this type of group. This is what the sulfonate is. For a mesolate, this is a methyl. For a triflate, it is a CF3. And for our old buddy tosylate, which is really the most commonly used one, it is a toluene ring. And so the reason that the triflates end up being the most reactive is that the CF3 is very electronegative. It's going to make a big dipole, which is going to take electron density away from this oxygen. So that means that this type of leaving group, and one way to look at the rates of reaction is how good is the leaving group. Do that poorly. This leaving group is going to be very stabilized because we have this awesome electron withdrawing group on it. So it's going to be able to really take electrons away from the O minus. And at the same time, it'll even polarize the neutral compound because now this bond wants to break more. In terms of relative reactivity, tosylate and mesolate behave pretty similarly. The tosylate's a bit more reactive just because of the electronegativity of this sp2 center on the benzene ring. Turns out that does make a small difference, but the main thing I would want you to know is that triflates are crazy reactive. Sometimes alkyl triflates are even hard to isolate because they tend to eliminate and do other things too fast. Yeah. Next one is exam 1, problem 3. So I just described this on Piazza. I can try to go over it again. When you are considering basicity, specifically weakest base, do you consider hybridization over aromaticity? Usually, if they're all the same atom, hybridization will be probably the most significant factor. The questions on the test will not make you compare hybridization and aromaticity. I would say that the questions related to acidity should be down to one major factor that you can distinguish between. In the end, hybridization usually wins. SP hybridized things that much better at stabilizing negative charge or destabilizing positive charge that they tend to dominate. Um, but if they all have the same hybridization, then things like aromaticity would probably be the next biggest factor. But in general, resonance is just kind of, I guess, a specific example of resonance. Yeah. But I was looking back, the acid-base questions, I think they yeah, I think there's generally one element that should make it stand out over others. We'll find out. But I'm going to get back to exam one. This is asking about which is the best, uh, or what is the least likely to be a nucleophile, and we had iodide. And this question came from topic two, I believe. We have phenol. Oh, my handwriting fails whenever it's particularly bad whenever I'm not looking down at my screen. So there's two ways to kind of look at this. One is like, okay, iodine is out because it's negatively charged. A way to approach the least likely to be a nucleophile in a way is just kind of looking at what reactions do we know with these compounds. Um, I mean, generally alcohols are viewed as nucleophiles. You never really see an alcohol as a leaving group, except I guess in the case of like E1 elimination, but even then it's going, or E1CB, and that's even a little bit, it has to be deprotonated first. But just, I would say that from the reactions we know, we can see this as being an awesome nucleophile in EAS. This is a great nucleophile in EAS. Methanol is a nucleophile in like general substitution reactions or like halohydrogen formation. Whereas this is really good for SNAR. It's an electron deficient aromatic ring. We have fluorines, we have aldehydes. If you wanted to try to identify what is the most nucleophilic part of each of these molecules, we're really going to be focused on these lone pairs. Though in EAS, it ends up being the carbons that end up being nucleophiles as well. So it's not always, because we use those lone pairs to go through the ring. We never really see a aldehyde act as a nucleophile. The best we see it as maybe a base occasionally, and that's sort of a reversible situation. You could say that this is sp2 hybridized, so it's going to be less nucleophilic and less basic than, say, the sp3 oxygen. But I think in this section, my thought process was probably you guys learned nucleophilic aromatic substitution, and aromatic rings are electrophiles in that case. Problem set 1, number set. Okay, this is a lot of writing. Okay, so this is talking about, yeah, the orange carbons are nucleophilic in addition to the para because like if an OH or an NH2 on a benzene ring is an ortho para director, and these end up being our highly activated systems for electrophilic aromatic substitution, in which they are the nucleophile reacting with the electrophile. Right, I will sketch some of these cases. Oh no, drop my yogurt. So this is asking to identify the least stable resonance isomer between two different things. So one case we have an allylic cation where we either draw it in a tertiary position or in a secondary position. And so this is tertiary and it's benzylic. So this is going to be more stable. This is less stable. So both of them are representative of the overall picture of the molecule. This is just the one that would be the less populated resonance isomer. We have one with this oxocarbenium ion also in its carbocation form. This one is the less stable because this carbon has an incomplete octet, where this has a filled octet, full octet. So this carbon only has 6 electrons on it. And this is actually a huge factor for resonance stability. You really want to have a full octet. Then we have just a neutral amide. And an amide in its charged resonance form. So they say the charged form represents about 20 or 25%, but this is the less stable isomer just because a neutral molecule will be lower in energy. Anytime you go to charged structures, they end up raising the energy, having localized charge in places. The more neutral it can be, the better. But I think this is still supposed to be like somewhere around 20% of this sort of resonance character. And the rotation around a double bond in an amide is really slow because of this sort of double bond character between the carbon and the nitrogen. We got one more. Ooh-wee. All right. And now we have sort of like the imine equivalent of an enolate, or you could view as a deprotonated enamine. And in this case, this is going to be the less stable isomer because carbon is less electronegative than nitrogen, and so it will be less able to hold on to this negative charge. This will still be a pretty reactive nucleophile. This would end up being much more reactive of a nucleophile than your average enolate is. Or electroneg. There we go. No more Piazza questions? Fuel. So each of these have a filled on this one? Or are you talking about this one? This is the only example that ends up having there are incomplete octets in carbocations, but both are have incomplete octets. So both this carbocation and that carbocation, one doesn't have an advantage. In this case, this nitrogen has 8 electrons, and this carbon has 8 electrons. Because we do still have the hydrogen here. They're the lone pair and the 3 sigma bonds. Yeah, so this is still a, because the carbon has 2 electrons from each of the covalent bonds, and then it has 2 electrons from this lone pair. So it's still an 8 electron species. Those carbocations you got to watch out for. Or boron. Boron is 6 electrons generally. Guys got any more? You guys feeling good? Ready for this? It's all going to be over soon. Less than 24 hours. Then no more organic too. So sad. Tears. I know. I'm crying over here. Though I get to come and teach this class again someday. So I know it's going to come back, get all new sets of people. Hopefully not the same ones again. All right. That wraps up people's questions. It's been a pleasure having all of you as students. Thank you very much. I know this has been a tricky end of the semester, but I think we're all going to make it. We're all going to do it. All right. Oh, can I briefly explain number 1 on exam 5? I can do this. Number 1. Oh, exam 5. No goodbyes yet. Oh, this one. I have this in a video. Did I make a video about this? I don't know. Maybe I just talked about it in class. I don't know what I've made videos of and not anymore. Oh no, this looks like I made a video of. So I will answer the question about enolates, and that is not a dumb question. So we have this molecule, and the main idea is that under basic conditions, it'll be in equilibrium with this enolate structure. And so we can actually draw this enolate reacting in a couple different ways. We could have the arrows coming down and attacking this way to react with our deuterium oxide. Or we could have arrows also go down and now go through this bond to take this deuterium oxide. So on the red pathway, we'd end up first making, this initial compound. It again could be deprotonated to make another one of these potential enolates that could then once again react at either this position or that position. So over time, it continually reactions at both of these sites until all of the hydrogens are exchanged for deuteriums. The thing to note is that it never puts the negative charge on this carbon in the middle. So that one ends up remaining as a hydrogen. If we go look at the orange pathway, we'll end up with the double bond being one closer, and we'll initially put one deuterium on. Again, this can be further deprotonated future times. So we'll continue to add more deuteriums to the end, and more to the end. And eventually we'll also go through the red pathway and we'll get a deuterium here. So this is how we end up getting all the deuteriums at one end and also one here in the vinyl position. But it'll still go through this enolate where the double bond's on the other side. Thermodynamically, the double bond wants to be in conjugation, so this is where it'll end up at the end of the day. There is not a case where deuterium is added around the ring, no. So the reason being, if you think about the pKa of, say, water's pKa is 14. The pKa of, say, a phenyl proton is, more than 45. Hydroxide just isn't strong enough to deprotonate it. If you added in sodium amide, then I don't know, I guess as a thought experiment, one way you might be able to do this is if you had NaND2 in deuterated ammonia. Oops, I can't even draw deuterated ammonia. My hand won't let me. I have never seen those reagents before because this would be a very strong base. And maybe that would be able to actually deprotonate a benzene CH bond. But the question on when an enolate will be formed versus something attacking the carbonyl, even though we have a lot of strong bases, our Grignards, our lithiums, these will always be attacking carbonyls. Occasionally we see something like phenyllithium act as a base, and this is like when we make a phosphonium salt for a Wittig, but we don't have any ketones around or else it would do that first. Actually depends on how acidic that hydrogen is, but that's a longer story. There are some very strong bases that we have, like amide bases, that are really bulky. These do not tend to add in to carbonyls and pretty much just deprotonate things. Butoxide is always a base. Sodium hydride is always a base. Those are the ones that you can rely on always being bases. Cool. All right, I'll check the Piazza one more time. Nope, nothing on Piazza. Sorry, win the something. When the second addition on the red pathway happens, where does the deuterium go? Um, what do you mean this deuterium? So if the OD deprotonates, we would end up making this enolate, and now there's a deuterium here. The byproduct ends up being DOH, where it's like monodeuteраted water. But since you have like a millionfold excess of D2O, the equilibrium will always shift to pretty much deuterating everything. And so now this will come back again. We're going to have another D2O. And once again, we're going to have the choice. We can have our red pathway happen again. And it might briefly make a deuterium where we end up with two deuteriums here. But the thing is, these are still acidic. And you can also deprotonate a deuterium. It's all an equilibrium process. So this is actually reversible. Or you could have our orange pathway occur. Where now the other side of the molecule gets deuterated. So these are all kind of shifting and exchanging. It always goes and progresses towards everything becoming deuterium, and the double bond ends up wherever it's happiest thermodynamically. Hope that answers the question. All right, I think the questions have probably slow. I'll still try to reply on Piazza tonight when I can. You guys have further questions? Otherwise, the exam will be up at 11:20 a.m. We'll have your 3 hours to do it. It's going to be great. You're going to get in there, do some organic chemistry. Boom. Everyone have a good evening.